A very good morning to all of you. Today we are at lecture 4 of Control Engineering in AI 5 section. Now what is the topic today? Introduction to block diagram of control. We have already gone through the control system basic concept. What is the physically present control system in the real world, and then from physical system that we have converted into the physical model. So then we have converted the physical model into for the analysis purpose we need the mathematical expression, the relation in between input and output, and that we have projected through the mathematical model. Mathematical model we have done already, and there were the two approach that we did. One is the what you can say the transfer function model, another one is the differential equation model. Okay, so that we did, that part we did. Now we are going to start the control system block diagram, because sometimes the control system that is represented in a complex manner that is present. And now we have to analyze that control system. We have to understand that control system, and that understanding that control system in a simple manner. There's a pictorial diagram that we are representing through the different blocks, okay, associated with the signals. That is nothing but the block diagram that we are going to study. Okay, so moving to the first slide, let's see what is the subtopic. The subtopics we are going to cover: what is a block diagram, basic concept of the block diagram that will be analyzed over here. What are the different parts of block diagram? Because we have to fully understand what is block diagram, what are the different blocks involved, and why they are involved like this way, that we have to understand. And then how to construct the block diagram, because what is our objective? Our objective is we need basically the complete understanding of the system. We have to map the complete physical system into the model through the block diagram. Okay, and the block diagram comprising all the mathematical expression involving with each block, and then as a whole that block will represent basically the mathematical model of the control system. That is nothing but the transfer function of the okay, that we will be studying, and through the example obviously we will be studying. Okay, now moving to that part. So what is basically block diagram? You are see, you can see that this one is the representation of the block diagram. Suppose, okay. So what you are observing that these are the blocks. Two blocks involves GS and HS. We don't know what is GS, we don't know what is HS, but we know that these are basically the Laplace domain expression, okay, Laplace domain functions that I can say, and this is nothing but that I am saying, telling to you, this is nothing but the transfer function of that complex circuitry involved in this GS. What is GS basically? GS is nothing but the process, okay, or plant, and associated with the control involved in that process, whatever be the attention unit, etc. There are the several subsystems involved in the GS. So it is a very complex system, but we are representing in a single block, nothing else. Associated with the input and the output, input array is representing here the input signal impulse or input or excitation, and the output here involves basically the output signal representing by the output array. Okay, here GS and this one is another signals. Okay, so GS involves two signals, similarly HS involves two signals. So here each of the block level representation, that is a pictorial representation you can say of any system. So we can say the representation of the control system block level. So it is we are not distinctly finding what will be the complex circuitry involved, what are the circuit elements, okay, what is the complex elements involved. We are only concerned about the transfer function of the system associated with the input signal and output signal, nothing else. Okay, so that's why this is the simplicity of the representation of through the block diagram. And one can easily project any system into the block diagram that we will be going to study. So what is basically involving with the block diagram? All the blocks we are telling these blocks are nothing but the transfer function of the system involves or subsystems involves in this system, and these there are the starting points there are the takeoff points. Now what is summing points? Summing points, so here referring this point. Summing means basically addition, subtraction, both operation. That will be done here happening. So where the RS is the input signal, this one is the feedback signal. Suppose this one is the forward path, right? And this one is the forward path, right forward path. This one is the feedback path and coming feedback path. Okay. So what is forward path? Basically, RS is representing your desired output or the set input. Okay. Set input. RS is representing basically desired output or the set input, and it is passing through the process controller, etc. There is a block involved, and subdivision of that block in the controller process. Okay, actuation unit are there, final control element will be there, then process. Okay, so all those functional blocks involved in a single block, that is GX, that is called the forward path, because input is here basically RS, that is the set input, and output is CS. So from direction from RS towards CS, that is called the forward path. Forward path. This is the general convention. Okay, so we are assigning a path coming from R to C, that is called forward path. Why forward path? It is the convention that is starting from the set point towards a control variable. It's control variable, right? You know, this is the control variable. That path is called the forward. Whatever be the blocks involved, we are considering only GS block, that is offering basically the transfer function of those forward of that forward system, of the forward path associated system. And this is basically feedback. Why feedback? Because you know that from the output means here the control variable. Okay, from the output towards the input, whatever way the signal is coming, that is called the feedback signal, right? And through the system, that is called the feedback system. And here the feedback system is representing the transfer function of the feedback system, that is nothing but HS. Okay. So this path starting from CS towards RS, that is called the feedback path. This one is the forward path and this one is the feedback path. Right? So we have already understood what are the paths involved. Fine. Now, the diagram involves basically blocks. These are the functional blocks, right? And these blocks involves basically the input signal as well as output signal, right? So each block involves the input signal and output signal, and that will be assigned with the weightage of the, what you can say, the transfer function of that system. Fine. Now, while uh, there may be the two signals, additively or subtraction will be done in between RS. Suppose this feedback signal, suppose it is conventional BS. Okay, so RS BS. What is the phase relation represented over there? This is plus, this is minus. If it is considered positive signal, that will be negative. So if this summation done through that point, and then what will be the signal? Signal is coming here. Suppose yes, air signal. Generally, it is the term. So it is RS positive phase signal, negative phase signal is VS. So RS minus VS, that will be the input to the GS, that block. Okay, processing block. So that's why here this point is referred as a summing point. So all the signals will be summed up over. So that's why it is called the summing point. That may be in phase, in phase or out of phase. Okay. So there may be one, two, or three, or more than three involved. Okay. And so that's why signals involves. So that's why it is called the summing point. And another point we may observe commonly, that is called the takeoff point. So what is takeoff point? So takeoff point means all the signals. See, there are the two parts of the signal. One is coming towards the output, another one is coming towards the feedback. So there are the two branches, branch of. Okay, so there are the two branches involved over there. So same signal is coming towards the, as a control variable, same signal is feeding towards the feedback network. So that's why it is called the take-off point. So signal will be taking from there. So that's why it is called take-off point. And the all arrows involved, representing over there, all the arrows involved. Okay, that is showing basically the flow of the signals, nothing else. So what we found in the block diagram, we found all the you may say those are the transfer functions of the subsystems of that control system involving with the input and the output signals and signals direction directly indicating over there. So those are the signal flow, nothing else. So involving with the summing point and the takeoff points. So this is nothing but the pictorial representation of any control system that is called the block diagram. Now I think that it is clear to you what is the block diagram, what are the blocks, what are the arrows. Arrows representing signals, arrows representing here signals and signals associated with the direction that is flow of that signals and all the blocks enclosed with the transfer function of that subsystem. Okay, so that is called the block diagram. Now moving to the next part. So what are the different parts that we have analyzed? Now typically we will analyze blocks. Basically, what is block? Blocks are representing over there the transfer function of the component is represented by the block. Rather say it may be a component, it may be a subsystem. Not exactly the component, it may be a subsystem sometimes. Okay, because in the forward part, wherever we are taking into consideration RS. Okay, that signal that will come first to the controller. Controller. Okay. Then it will come to the generally actuator. Then it will come to the final controlling unit, right? Then it will come to the processor plan. So see, there are so many subsystems in the processor plant. Really. So which parameter we are controlling? Okay, the physical parameter we are controlling. Then it is coming as a control variable. Okay, so see what are the subsystems involved in this forward part. Not only the process having the final control element, actuation unit, controller. So as a whole, we are representing this one as a GS, the system. Okay, so system involving with the input XS and system involving with the output YS. This is represented by the blocks. Okay, so it may be a component, it may be the series of components, it may be different combinations of components, it may be the subsystems. Better to say subsystems. Okay, then what we can say here, the blocks having the input XS and the output YS. And it is nothing but the transfer function of that systems or subsystems. Okay, let me clear my sketch. And now see, what is the transfer function in S domain obviously? Taking the Laplace transformation of input and output and taking ratio. So YS output, Y input, that will basically tell you basically GS. Okay, and then what is YS? So it will be GS. Okay, correct. So YS will become GS by S, right? YS will become GS into XS. So that is basically YS and YS become GS into XS. So output of the blocks is obtained by multiplying the transfer function of the input is domain, right? As well as the transfer function and the input capacity. So that's why it is nothing but YS. So we are reflecting here the blocks associated with the transfer function, input signal, signal investment. Now moving to the next step. Let me clear all those things. Moving to the next. So what we have here, the summing point. Summing point is represented with a circle. Let's see what is the representation of the summing point. Is the circle with cross, right? And having two or more input signals. This is representing two signals. This is representing three signals. Okay, and having with the algebraic sum of the input or it may be difference. Okay, so sum of the input it may be taken as difference. Because what is the phase relation in between A and B? That is reflecting over there, right? So here signal A and signal B, those are coming in same phase, positive sign. So that's why what will be the resultant? Resultant will be y equals to a plus b. Plain and simple summation of these two signals. Okay, that will be done to the summation. The algebraic sum will be taken. Similarly, if the signals are coming in just phase opposition, out of phase, so what will get? A and this one is B, that is minus B. So here the difference will be taken. Now for the multiple signals, this is the summing point that may be represented over there. A, this one is B, coming in same phase, and C in opposite phase. So what will be Y? Y will be A plus B minus C. Nothing else. It's simple algebra. Okay. Now moving to the next point. So what is the takeoff point? Let's see. Takeoff point means that point from which the several signals, same signals are branches of the different towards the different blocks for the system. You can see. Okay, so takeoff point is a point from which the same input signal can be passed through more or two branches, more than one branches. From takeoff point, we can apply the same input to one or more blocks. So yes, blocks mean basically there in the subsystem, so involved. So this is basically takeoff point. The same signal will be consistent. So you can say all the signals are coming parallel to the each and every subsystems over there. Okay. Now, take-up point that may be towards the input side as well as take-up point that may be towards the output side. Generally, take-off point, what will be our consideration? That is coming from the output to the feedback part. One signal is coming, another signal is coming towards what you can say, towards the control behavior. So these are the two different directions, but same signal will be touched. As a whole, CS is coming to compare with RS, that is also called the comparator. You can say summing point. Okay, in analog, you can say it is comparator, nothing else. So you can design the comparator also, and that will be utilized here also. So whatever your knowledge of analog, that you can easily implement over there. Okay, electronic control system to build an electronic control system. And here is also this the takeoff point. So you are same signal will be branches at that point. Okay, so it is nothing but a node. So you are taking two signals over there. One is the control variable, another one is the feedback signal. So it is nothing but the takeoff. So here we are moving to the next part. Now we have already analyze what is the takeoff point, what is summing point, how it is coming all the signals, how the manipulation or algebraic sum or difference will be done, and then what is the transfer function input and output relations, and then what are the different basically the how to represent basically clocks. So these are common basic concepts we have already gone through. Now moving towards that part, how the actual network or circuit that will be created with a block diagram. Okay, so the topic is how to construct the block diagram of the control system. Control system we are representing over there a plain and simple RLC series network, and then we will be moving to the complex control system. This is to build up the basic concept. So each and every system having, we can say finally, whenever we are disintegrating any system, so we will get finally the components, right? And if we are considering any system into electrical equivalent, so we are getting RLC components. So for each and every system, if we have to equate into a circuitry, so ultimately we are getting three components, major, R, A, and C. So that's why I am taking this example. So each and every system, you can say it is not a difficult one to understand, having with the resistive effect, inductive effect as well as the capacitive. If there is any lagging, so it may be created as inductance that we have already iterated. Huh? If there is an inertia, that will be equated as an inductance, like that. If there is any capacity that involved over there, so that may be represented as the capacitor. If there is any you can say obstruction, damping, so that may be equated as the resistance that we have already done. Okay, so that's why each and every systems finally, if we disintegrate, what will get? We will get different types of components. So that's why I am taking this example. So how to construct the block diagram of plain and simple RLC system network, that will be explained over there. And then there will be new metals and we will solve it in the next class. Okay. So consider a series RLC circuit where what we are getting here, VIT as the input signal and VIT as the output signal. Okay. So VIT is here input signal and this is the time domain circuit. So what is the current flow? IT. Right. So it is plain and simple representing time domain circuit. What is the circuit? That circuit reflecting time domain. Fine. Now, what is the first and foremost requirement? That it is time domain set. Fine. So what is the input here? Input is the driving voltage, VIT, and what will be the output? We are considering output voltage against the capacitor while current is passing through the capacitor side. Fine. So output voltage is against the capacitor, and that is VIT. Now, what is the first step? First step we have to consider in case of block diagram, what we need? We need basically the transfer function. So to get transfer function, what is the first step? First step we need to take this circuit into is time domain circuit into S domain circuit. Okay, which means Laplace transformation that will be done. So S domain circuit, plain and simple, we can draw R will be equated to R in S domain. L will be equated to Ls because it is the impedance Ls 1 by omega L, right? So it's domain j omega L you can say. So it is Ls. Okay. And in case of C, what is the capacitive impedance? Capacitive impedance is 1 by j omega C. So that may be equated as 1 by SC j omega, right? So S will be basically here j omega for the steady state. That will be clarified later on. Okay, for the steady state analysis, S will be considered as j omega. Okay, and S equals to basically j omega plus sigma, right? S equals to sigma plus j omega. That part is the transient part analysis. So here, while we are considering basically what you can interpret it in here is also as we will consider the frequency response analysis suppose. So in that case, the frequency will change. Okay, so what will be the change in S? That will be reflected to the frequency. Okay, so with respect to the variation of S, we are analyzing all these things. All the signals are basically the functions of function of S. So that's why S equals to j omega we need to put in case of steady state response because they are transient to over. So this and alpha part is over. That's why we are neglecting this one. This will be written as j omega. So what we get in S domain we are getting here instead of j omega we are getting S. So Xc will be equals to 1 by Sc and here j omega L that will be equals to impedance suffered by the inductance that is Xc. You can remind in this way. In this simple manner you can remind. Okay. So we are analyzing basically steady state. So while we are getting this equals to j omega, keep it in mind, it's very much important concept that is this equals to j omega steady state response to nothing else. Okay. So why we are not considering sigma that part. Okay. So here, just let me clear all these things. So what we need the estimate circuit. That's why time domain circuit will be converted into estimate circuit. So here, uh, I that will be considered as IS, right? And VI that will be considered as VIS, and this one is VOS because all are in estimate function. And these are functions, these are the parameters. So parameters reflecting the impedance R will not change with respect to the frequency, and S will change, L will change LS, and C will change by the amount 1 by SC, right? Now, as we have to get the transfer function, so we need basically IS to get the output voltage VOS. So what is IS expression? VIS minus VOS divided by R plus LS total impedance, R plus LS plus 1 by, okay, okay. So that is the total impedance offered by this capacitor that should be modified, right? 1 by SC. But here In case of block diagram, we have projected the S-domain circle. Fine. Now, what will be the next step? So, how to reach the block diagram of this network? Okay. So let's find what is the step 2. Step 2 is write all the equations taking left to right in consideration. Left variable as driving function and right variable as resistance. What I'm talking, that is the each and every equations. Equations means relation in between driving function and the response. Input and output. That you have to write, right? Okay, fine. Let me clear and then again try to understand. Now see, as it is the IS, right? Is a response of VIS, right? So we have identified two variables. One is input, another driving function, another one is the what you can say the response. So what is the relation in between VIS and IS, right? So just try to get it. Okay. So if we consider here this one is VIS node and this one is VOS node associated with the voltage VOS, this one is VIS. So gradually if we progress, so what we can calculate here the relation in between VIS, VOS and IS. So what is it? IS as a response, IS as a response, and this one is the driving voltage. So VIS minus VOS divided by R plus LS. So first equation that we got, that is a relation IS equals to VIS minus VOS divided by R plus LS. This is the equation number 1 we have to obtain. Okay, and that will be projected, that will be mapped in block diagram question. Okay, that will be mapped in block diagram. I'm coming. So this one is equation number 1. Let's consider. Now once we get IS, now we have to build up VS. So at that period, at this time, we have to consider here IS as a driving variable, okay, that is input, and whatever VOS we are getting, that is the response. It is the excitation, and that one is the response, right? So, if Is is the flow through the capacitor, then what will be the voltage drop? Vs will become 1 by S into Is, right? That is the output voltage. So, we can represent Vs in terms of Is. So, what we get? Vs equals to 1 by S into Is. So, plain and simple, you have to get two equations. You are getting two equations, sorry. You are getting deliberately, you are getting two equations. How what will be your objective? That is left variable is the driving function and right variable is the response. Keep it in mind. So while left variable is the driving function, right variable that is the response. Similarly, left variable is the driving function and right variable is the response. So like this way you have to construct the algebraic equation. Plain and simple, algebraic equation you will get as because it is S domain, so you are getting the algebraic equation, fine. So you are getting the two equations. So with these two equations, we want to map this network, this practical circuit into the block diagram. So we are moving from the actual network to the block diagram. Okay. So what is the two equations? What are the two equations we are going to use now? Equation number 1 and equation number 2. This two equation we are going to use. Okay. The first step is to derive the block diagram. First one is domain network unit. And what is the second consideration? Second consideration is try to understand all the variables of the S domain. Now, which one is the dependent variable? Which one is the independent variable? So, generally, left is the independent variable, right one is the dependent variable. So, represent over there the variables, what is the dependent and which one is the independent. And try to get the relation in between the dependent and independent, each variables you have to consider. Which one is the cause, which one is the effect. Then that effect will become the cause for the second stage and that is the effect. That effect will be the cause for the third stage and next will be that. Like this way, you are continuing continuously series in a serial manner. You are continuing. So what you get, you are getting here two questions. Fine. Now moving to the next part. Let's see what we have. So equation number one is implemented with the block having the transfer function 1 by r plus s. Fine. See the equation number one. What is the equation number one? VIS minus VS divided by r plus ls. Fine. So moving towards this one. So what we have here? VIS minus VS. Okay. VIS minus VOS that you have to implement divided by R plus LS. Okay, so that is equals to IS. So how to represent? IS we have to represent. So this one is basically IS we have to represent. Okay, sorry, IS we have to represent. So what we have VIS minus VS that will be accomplished. So we're starting with a summing point. But because we know what is summing point. So what is summing point? This is VIS and this one is VOS. So VIS minus VOS that will become basically direct signal over there and that will be multiplied with 1 by R plus LS. So it is these are two signals that will be manipulated through this summing point and that is in phase opposition. So we are putting here plus and this one is minus. So what is it? VIS minus VOS. Now what we have to employ the gain. So gain will be in the block with the weightage. That is the transfer function of that block. That is 1 plus R plus LS. So we are putting here 1 plus R plus 1 by R plus LS. Okay. And with the input VI minus VOS. So what is the values? So finally the equation number 1 that will with the help of a summing point and the block with the transfer function that is written over there that is representing equation number 1. Okay, that is representing equation number 1. So we are getting here the representation of a part of block diagram that is representing equation 1. Okay, fine. Now we are moving to the see, what is equation number 2? Try to remind U is equals to 1 by SC into IS. Very simple. So IS we got, till IS we got as equation and that we have predicted in the block diagram. Then we have to represent the VOS. So what is VOS? 1 by SC IS, right? So moving towards that part. Let's see. So once we got IS, then coming to that part, IS having the transfer function, what we have 1 by SC. IS VOS becomes IS into 1 by SC, right? What was the equation? Equation number 2, VOS that is basically IS by SC, right? So what is the transfer function? 1 by SC into IS, right? So IS is a signal and the transfer function is 1 by SC that is written in the block. So what we have here, US is becomes 1 by SC into IS, right? So just combining these two, equation number 1 and equation number 2. So first block till that part, okay, and second block IS we got, and second block that is VOS we got. Now, as that signal was led to VOS, right? That was VOS. So simply we have to manipulate here. We have to take here a take-off point, right? As this is the take-off point, so there is the branching of the signal in two paths. One is towards the output, that is basically VOS over there, and towards the feedback path with the unity gain. Because see, what we have the manipulation VIS minus VOS. So that's why as a whole VOS that is passing through that feedback path and with the negative sign. So what we are getting here? Plus minus then VIS minus VS. So it is a complete closed loop circuit that we have finally formed. For RLC network, if it is a system, we have to represent in a block diagram. So what we are getting here? VIS as the input, VS as the output, and we have two blocks involved with the gain 1 by R plus LS, another block involved with the gain 1 by SC, and here two points. One is the comparator, that is the summing point involved over there, and another one is basically the takeoff point involved over there. So in this way, we are getting the block diagram. Okay, by just mapping the equation number one and equation number two for RLC series network. For RLC series network. Okay, so see the equation number. For equation number 1, we got this part, and for equation number 2, we got this part, and we are combining both of these two. So we are getting this one is the final diagram. This one is the final diagram. Okay. So what we have here, we have here the block diagram of simple RAC network. Okay. So in this manner, any circuitry, if we have given, then we can easily transmit into the block diagram. Okay. Let's see. Again, I am repeating that part is very much important. So which part? We have fast conversion in the S domain, that is very necessity. Number one, that is very necessity. Okay. Time domain function, that will be converted, time domain circuit, that will be converted into S domain circuit, that will be converted into S domain circuit, and then you have to find the relation among all the variables. Now how to get the relations? There's a path. So how to get the relation? You have to consider all the driving variable, which functions will be as a driving function or input function. That will be all the starting from the left towards the right. We are moving. Left means from the input towards the right output. Okay. So input, any input signal, that will be considered as the driving function, and any right-sided signal, that will be any immediate right-sided signal, that will be considered as a response. So like this way, for each and every input we have to identify, each and every response we have to identify. And what is the cause and what is the effect, we have to identify. And then positive relation, that will be represented through the equation. So one, two, three or more equations if we get, and then we have to draw for each and every equation we have to draw the block diagram, and then combine all those block diagrams, sub-blocks, basically sub-block diagram, and then combine all those block diagrams, so we are getting the final. That's very simple. Okay. So as summary, we can represent here. So what are the steps? Draw the block diagram of any electrical circuit or system just by following the simple procedure. What is the process? Convert the time domain electrical circuit, time domain circuit into S domain electrical circuit by applying the Laplace transform. Very simple. Each and every, it is very simple. Each and every signals that you have to write as a function of this, and each of every parameter of the time domain, that will be equated in the S domain parameter. So only there is a change for the capacitor or inductor, resistance will not change basically, because a pure resistance having the no effect in the with respect to the change of frequency. So only the capacitors and the inductor involves the changing, and write down the equations for the current passing through all series branches, elements, and voltage across all the shunt branches. That means you are considering for the series branches, you are mainly considering the current, and for shunt branches, you are considering also the voltage as well. And draw the block diagram for all the above equations individually. Individually, draw the blocks and then combine all those block diagrams properly in order. Because starting from the left to right, we have considered. So each and every should have to be mapped into the block diagram, and then we need to combine all those diagrams to get the overall block diagram of the electrical circuit or the S domain in the instrument. Obviously, the block diagram representation in the instrument. Okay, so these are all steps involved, so you have to keep in mind, and it's very simple. And we will be drawing the block diagram of the network. Okay, examples, more examples that will be given to you, and us how to reduce the diagram into a single diagram. That means whatever you have, uh, this is the diagram. Okay. So what is the overall transfer function you can find over there? So you have to manipulate it. Okay. This one is the total. What will be the total transfer function of the? As we say, what is the total transfer function of the system? That means you have sketched you have mapped the circuit into the block diagram. So in a simple manner, you have converted all the integral differential equation in the linear algebraic equation. That as because you are using the Laplace transformation, very much interesting and simple to actually represent all those things. And also you are analyzing in the S domain sometimes, or you are converting again Laplace, taking Laplace inverse transformation. You are converting again the output into the T domain. So for this case, what you have to represent a single block with the total transfer function of the system. Yes. Okay, where the output ultimately will be VOS and the input will be only VIS. We don't know what is the internal subblocks, what are the connections that are made. So we are getting only the total transfer function, and there is a mechanism that is called the block diagram reduction technique. So all the blocks will be reduced into a single block, and we will be getting the transfer function in the way. There is a very step by step, or you can say is a elaborate process that will be discussed in the next class. And what we will get VIS, VOS, and only TS. So we may represent here VOS that will become VS into VIS, right? So in S domain, we will get the complete output expression. Now in S domain, that will be real domain that we have to transfer. So that's why Laplace inverse transformation that will help us, and then we will get the expression of UT in time domain, in real domain, and that will be the function of t. Then we can just when we sketch the graph, as well as we may draw all the records of those POT, and then we can draw the graph or analyze the characteristics of the system. Like this way, the system will be analyzed. So that's why block diagram will be helping you to analyze finally to get the transfer function of the system as a whole, and then we can that will also help us to analyze the representation of the system in simple manner, and that is the work of block diagram maybe. Okay, now, so that's why this is advantage of the block diagram. You can say this is very simple to look as well as analyze. Okay, and while we will be going through the block diagram algebra, we will be getting the concept that it may be very simple to get the transfer function of the system, but it is too tedious process. That's why there may be another other processes that will involve to get basically the transfer function, and that will be uh, actually that is the progress of the from whenever we are getting some disadvantage of any analysis, then we will be moving forwards towards the next analysis process, and that will be much more simpler, right? Simpler. So that's right, and that will basically help us. Okay. So thank you for today. Have a good day.